Now we would have a discussion about relational algebra and relational calculus. Well, basically the query or the SQL that we write, they are basically governed by both the relational algebra and the relational calculus operators. Or in other words, we can say that the answers that we get out of the queries are as a result of the relational algebra and relational calculus, right? So for example, if we write something like select static from EMP, so we are using relational algebra behind the scenes to execute the query. So in this discussion we would be having a little inside details of basically what those operators are for relational algebra and relational calculus. First of all, some points. The inputs and outputs of a query are relations, right? So we give an input to a relation and we get the output of the query as a set of relations. So a query is evaluated using instances of each input relation and it produces an instance of the output relation. So query is evaluated using input instances of relations and produces an output instance of the relation. We are going to be having the discussion by using these examples of these schemas. Okay, we will be having a Sailor schema where SID is an integer, Sailor ID, Sailor name, rating, age. Then we have the boats with the boat ID, boat name and color, and there is the reserves, Sailor ID, boat ID and day. Reserves gives us which sailor has reserved which boat which sailor has reserved which boat on which particular day. So this is basically how we are going to be operating. So now let's proceed and we can take a look at basically the types of things, right? So this is basically the official representation of these relations. For instance, S1 of sailors, S2 is also of sailors, and R1 is of reserves. So R1 has got SID, BID, which is the primary keys of S1 and the boat. Boat table has not been shown, but boat is also a table, boats. So what do we do in relational algebra? Queries in relational algebra are composed using a collection of operators. So a fundamental property is that every operator in algebra accepts one or two instances as arguments and returns a relation instance as a result. So every operator can take one or two inputs and it produces one output instance. This property makes it easy to compose operators to form complex query, which is basically a relational algebra expression is recursively defined to be a relation, a unary algebra operator applied to a single expression, or a binary algebra operator applied to two expressions. So we can have a combination of unary and binary applications of these operators. So we'll be describing the basic operators of algebra, that is selection, projection, union, cross product and difference. So these are the basic operators: selection, projection, union, cross product and difference. And additional operators can be defined in terms of these basic operators. So each relational query describes a step-by-step procedure for computing the desired answer based on the order in which the operators are applied to the query. So the order of application of the operators is important to the answer. The procedural nature of the algebra allows us to think of an algebra expression as a recipe or a plan for evaluating a query. And relational systems use algebra expressions to represent query evaluation plans. So one important point would be a query evaluation plan, which would depend on basically the type of the operators and the order of the operators. So what do we mean? That the order of operation might be changed by the query optimizer if the result just does not change. So that is an important point. So we start with the basic operators selection and projection. So relational algebra includes operators to select rows from a relation, which is denoted by sigma, and to project columns, which is represented by pi. So these operators allow us to manipulate data in a single relation. Selection is basically the select operator that we use, and pi is basically the number of columns that we project or we have the answer of. For example, so we are having a selection, and what is the criteria of selection? Rating should be greater than 8, and which is the input instance? It is S2, right? So we select from S2 and project select from S2 and display all the rows which satisfy the criteria that rating is greater than 8. So we can go back and see S2, which is S2, and basically which rows would be selected? This one, this sorry, not this one, this one and this one. So these two rows would be the output of this particular query. So these two are the outputs. So after selection, the projection operator pi allows us to extract columns from a relation. For example, we can find out all sailor names and ratings by using projection pi. So what we can write? We can write pi project sailor name comma rating from relation S2. So from all the fields S2, we are just projecting sailor name and relation. So this is the answer of sailor name and rating, sorry. So this is the answer of this particular projection operation that we are having. Similarly, if we wanted to find out only the ages of the sailors, the expression would be projection age S2. So these two ages are displayed from the relation S2. So in this instance, what we are doing? We are first selecting all the rows in which rating is greater than 8, and from that result we are projecting the sailor name and rating. So remember what was the result of this? 2 complete rows. So from those 2 complete rows we are just projecting the sailor name and rating. So this is basically the answer. So now we can look at some set operations that are of interest to us. The following standard operations on sets are also available in relational algebra: union, intersection, set difference, and cross product. So what is union? Union S returns a relation instance consisting all tuples that occur in either instance R or relational instance S or both. Just like set operations. But for this thing to occur, R and S must be union compatible. And what do we mean by union compatible? The two relations are said to be union compatible if they have the same number of fields. So total number of fields are the same for R and S, and corresponding fields taken in order from left to right have the same domains. So the type of the total number of fields should be the same, and the type of the field should be the same when we are reading from left to right. So these are the two important conditions. So let's look at S1 union S2, right? So this is S1 and this is S2. So can we think of S1 union S2? This row would be included, this row would be included, this row would be included, yeah, this one and this one. So total there would be 5 rows in the answer, yes or no? So these are the 5 rows as already discussed in S1 union S2. Now let's look at intersection. R intersection S returns the relation considering all tuples that occur in both R and S. So what were the tuples in both R and S? Right? Sorry, S1 intersection S2, right? So S1 intersection S2 would include Luba and Rusty, the 2 rows. So these are the 2 rows. Now we can have the set difference R minus S. All rows that are in R but not in S should be returned, right? Which is the only row? Thus 10 is included in R but it is not in S. So these are the set operations. Now Cartesian product is R multiplied by S, the number of tuples of R multiplied by the number of tuples of S. This is basically the answer. So if I want to execute S1 into R1, right? So how would that operate? This is S, this is R, right? So this row and this row, this row and this row, followed by this row and this row, and again this row and this row, followed by this row and this row, and this row and this row. So this would be the answer. So we can verify this answer in the output of this thing. You can see this row, first row and the second row combined with the first row and the second row, third row combined by the first row and the second row. So this is the answer of the Cartesian product. Usually Cartesian products are formed when we don't include the join condition. So if we create a join and we don't include the join condition, then also we are going to be having a Cartesian product in a relation. Now we can look at the renaming operator, and renaming operator is defined by row. So this expression, right, renaming operator takes the output of this operation and renames it to a new name. So in this expression basically we have this cross product. The answer of this cross product is over here, and it is denoted by relation C, and the relation C has been applied with the renaming operator. And what does this renaming operator do? In relation answer C, field 1 is renamed as SID1 and field number 5 is renamed as SID2. So if we can look back, this would be renamed as SID1 and this would be renamed as SID2. So that is basically the result of this renaming operator, and this new relation would be called C, and this is denoted as this particular answer. Now let's talk about joins from the relational algebra point of view. So join operation is one of the most useful operations in relational algebra and is the most commonly used way to combine information from 2 or more relations or 2 or more tables, like we said before, right? So first we have the condition joins. The most general version of the join operation accepts a join condition C and a pair of relation instances as arguments and returns the relation instance. The join condition is identical to a selection condition in the form. The operation is defined as follows, right? So we have this R multiplied by S, which is again a Cartesian product, but we have this selection operation and we have this condition C. So this is basically the condition C, which is the join condition, and it is denoted by R joined with S and with condition C. So we can have this, look at this example, right? S1 is joined with R1, and what is the joining condition? S1 dot SID should be less than R1 dot SID. So S1 dot SID should be less than R1 dot SID. So S1 dot SID should be less than R1 dot SID. So no, S1 dot SID should be less than R1 dot SID. So basically this would be one combination. Then S1 dot SID should be less than, this won't be selected, 31, 58. These two rows would be selected. So 22, 58 and 31, 58 should be selected. So 22, 58, 31, 58 is selected. Okay, so that's the answer. Now let's look at equijoin, and equijoin basically is a common special case of the join operation R joined with S, in which the join condition consists solely of equalities connected by this operator, and the form is R dot name 1 equals S dot name 2. So these two fields are equated, that is equalities between two fields in R and S. In this case, obviously there is some redundancy in retaining both attributes in the result. What does it mean? This attribute is equal to this attribute, so it would be redundant to display this attribute as well as this attribute in the answer. So what do we do? For join conditions that contain only such equalities, the join operation is refined by doing an additional projection in which S dot name 2 is dropped, and this join operation is called equijoin. Remember where we selected S dot DEPT number, EMP dot DEPT number equals DEPT dot DEPT number, right? So DEPT number was displayed once. So this is basically the end product equijoin, where the common field which is equated, where that was the DEPT number, was displayed only once. Let's see. We illustrate. This is the illustration of S1 joined with R1, where S dot R dot SID equals S dot SID, and this is shown in this figure 4.13. This is the join operation. So what do you mean this SID is only displayed once? It might be for S1, it might be for R1. So that is the whole idea. We can now look at a natural join, and natural join R joined with S is an equijoin in which equalities are specified on all fields having the same name in R and S. So whenever we have a natural join, we don't specify a field. The field specifies for all the fields with the same name in both R and S. So in this case, we can simply omit the join condition. The default is that the join condition is a collection of equalities on all common fields. So all the common fields would be created for this join when the natural join is concerned. So we call this a special natural join, and it has the nice property that the result is guaranteed not to have two fields with the same name, right? Like in the equijoin, remember, we refined it by using only one instance of the common field. So this same argument applies to the natural join. So of course we have this equijoin operation, S1 joined with R1, where R dot SID joining condition is R dot SID equals S dot SID. So can we call it a natural join? The answer is yes, because it is only SID that is common to both S1 sailors and reserves R1. So we could have simply written as S1 joined with R1, since the only common field is SID. So what happens if there is no common field in S1 and R1? Or in general, what happens if we join two relations and those two relations do not have a common name? The simple answer is we get a cross product. We now look at division. The division operator is useful for expressing certain kinds of queries. For example, find the names of sailors who have reserved all boats. So this is an important query that can be resolved using the division operator. Now let's see how. Let's take an example. We have this relation A, where we have the sailor number and P number fields. Okay. And then we have relations B1, B2 and B3. B1 consists of P2, B2 consists of P2 and P4, and B3 consists of P1, P2 and P4. So now we can compute A divided by B1. And what does A divided by B1 means? All answers that contain B1. All relations that are occurring with the B1, which is P2. So S1 is occurring with P2, S2 is occurring with P2, S3 is occurring with P2, and S4 is covering with P2. So we have S1, S2, S3 and S4 in the answer, which is this. Okay. Now let's look at A divided by B2. Now B1 contains P2 and P4. So we look for entries of sailor number entries that are appearing with P2 and P4. So first is S1. Why? S1 is appearing with P2 and S1 is also appearing with P4. So this is one entry. Which is the other entry that is appearing with P1 and P4? Is S2 answer? No. Because S2 is only appearing with P1 and S2 is not appearing with P4. What about S4? Yes, S4 is appearing with P2 and S4 is appearing with P4. So what is the answer? S1 and S4. Now B3 contains P1, P2 and P4. So we find the S number that appears with P1, P2 and P4. So is S1 the answer? P1? Yes. P2? Yes. And P4. Is there any other candidate that is appearing with these three? P1, P2 and P4? No. So the answer is S1. So these are the three relations. S3 is of sailors, R2 is of reserves, and B1 is of boats, right? So let's try to work out some queries in relational algebra. So we have to find the names of sailors who have reserved boat 103, right? So what you can find? We can first find the SIDs of the sailors who have reserved boats 103. So we first execute selection where BID equals 103 from reserves, right, which returns a series of tuples. We then have the natural join with sailors, and from the answer we project only the sailor name. So let's do it one by one. Let's first execute this one from reserves where BID equals 103, right? So what would be the answer? This tuple, and this tuple. So 3 tuples are selected, right? So 3 tuples are selected as shown in over here. Then we'll have the natural join with scalars, and the natural join with scalar means that all SIDs with the same values from over here would be selected, right? So SID of 22 would be selected here, SID of 31 would be selected over here, and SID of 74 would be selected over here. So what we have actually done is that we have renamed the first answers to temp 1. So this becomes temp 1. Then we execute the natural join of temp 1 with scalars, and we call it, by using the rename operator, to be temp 2. So whatever we do over here is basically temp 2. So afterwards, when we have this temp 2, we project the scalar name from temp 2. So scalar name is Dustin, Luber, and Horatio. So this is the answer. Final answer will be Dustin, Luber, and Horatio. So now we have to find the name of sailors who have reserved a red boat, right? So we have to find the names of the sailors who have reserved a red boat. So what we must do, we must have selection from boats first, where boat color is red. So all rows where the boat color is red would be selected, right? And what will be the answer of this? 102, this row, and this row, 102 and 104. So these two rows would be naturally joined with reserved, and it will be naturally joined with sailors. So we'll have all the rows where red boats have been selected by the sailors in these. I invite you as an exercise to write the tuples that would be appearing over here. So we'll have the natural join with reserves, and then we'll have the natural join with sailors. So when this part of the query is selected or is executed, what do we have? We have this row selected and this row selected. Now we have this natural join with reserves. So all rows of 102 and all rows of 104 would be selected. So this row would be selected, this would be selected, this would be selected, again this would be selected, and this would be selected. Total 5 rows would be selected. So after those 5 rows have been selected, finally we'll have this natural join with sailors. So 22 would be selected, right? 31 would be selected, and 64 would be selected. So finally we have these 3 rows, right? This one, and this one. So what is the answer? Dustin, Luber, and Horatio, because we are projecting only the sailor name.